Alright, so we're going to try this video lecture. Hopefully you guys are enjoying your little bit extended spring break as well. Let's have at it. What we're going to start talking about today is selection. And anytime we're talking about selection, of course, we have to be talking about, most appropriately, fitness. And remember, we think of fitness as the number of offspring an individual reproduces. Now, selection works on the genotypes, and we're going to focus on a simple system with two alleles at one locus. So if we only have two alleles, we can only have three different genotypes. We can have our homozygotes for the P allele, we can have our heterozygotes, and we can have homozygotes for the Q allele. Now, when we talk about fitness, we're going to need to find a way to incorporate this in a mathematical concept so that we can use it in our equations that we're going to need. So fitness needs to have its own variable, and we represent fitness all the time with a W. Now we have three different genotypes. We're saying that we're working with selection, so obviously our fitness is going to have to be specific for each one of those different genotypes. And we represent that by using the variable for fitness subscripted with the genotype, so that the fitness of the PP genotype is represented by WPP, the fitness of the heterozygote is represented by WPQ, and the fitness of the QQ homozygote is represented by WQQ. Now we can look at the relative fitnesses of these individuals by comparing their fitness values, or what their value is at WPP. If we start out and we look at selection for the dominant allele, we're going to say that P is our dominant allele in this situation. That means that these two genotypes are going to produce the same phenotype. Since selection is acting on the phenotype, what does that say about what's going to have to be true about the relative fitness of our homozygous for P individuals and our heterozygotes? Well, since selection is working on the phenotype only, these individuals have a P phenotype because that's the only allele they have. These individuals will have a P phenotype as well because they have a dominant allele P, so it doesn't matter what their other allele is. So these two fitnesses are going to have to be the same. They will be equal to each other. But now we can contrast that to what we have at the QQ genotype's fitness. Since we are selecting for dominance, then an individual with a dominant allele must have a greater fitness than individuals without it. So we could represent it as the fitness of WPP is equal to the fitness of WPQ. Both of those are greater than the fitness of the QQ individuals. So if you had a choice and I asked you what genotype you wanted to be, you wouldn't care as long as you had at least one of those P alleles, because your fitness would be exactly the same, and in both cases it would be greater than what we have for the WQQ individuals. Let's stop for a minute and think about this graphically, what this also means. If we were to look at what's going to happen to the frequency of the A1 allele, and remember, the frequency of the A1 allele is just P. So if we look at what happens to the frequency of that A1 allele over time, what should happen to it? Well, the P allele provides you with a phenotype that allows you to have more individuals than if you don't have a P allele present. So theoretically, everybody with a P allele, whether they're homozygotes or heterozygotes, will be having more individuals than those who only have a Q allele, or QQ homozygotes. So if we think about it, what should happen over time is that P allele should increase over time. It should get larger and larger and larger. But since P is a frequency, the maximum value it can ever reach is 1.0. It can't get greater than that. So we would probably suggest that the P allele will eventually reach 1.0 or fixation. Fixation is when there's only one allele in the population. So since P is the most fit allele, we would expect it probably to reach fixation. However, if we actually looked at it over time, what we would see is that, yeah, it does start increasing, but it never quite makes it to 1.0. It asymptotes. To 1.0. That means it gets close to 1.0, but it never reaches 1.0. So why does that happen? How can selection allow the inferior Q allele to persist in the system? Well, the secret are these guys right here, are heterozygotes. The problem is selection can see a WQQ individual and it can say, I don't like those guys. I want to get rid of them. They're going to go down. And it can see WPP individuals and it says, yes, I like those guys. So the question then, though, is what does selection do when it sees a heterozygote? Well, in reality, all it sees is the P allele. It can't see the Q allele. So it says the WPP individuals are good and the heterozygotes are just as good. So we can never actually lose the Q allele because it hides in these heterozygotes. What selection sees is just that first allele. As long as it's a simple dominant system, as soon as it sees one dominant allele, it doesn't care what the other one is. They all look the same to it. So our homozygote for P looks exactly the same thing as our heterozygote for P. So what ends up happening in selection for a dominant allele is we get what's called hiding in the heterozygotes. That's to say that the worst allele, Q, hides in the heterozygotes, or the A1 allele. So when we think about what's going to happen over time, our allele frequency is going to increase over time. It's going to get closer and closer and closer to 1.0, but it's never going to reach 1.0. So let's think back for a minute. We're just going to redraw our graphs as to what should be happening. Over time, the frequency of P should increase in an asymptotic way up to 1.0. Now, let's also try and think about what's happening to the fitness in this population over time. So if I were to do the same thing, and this time though we're going to take time and we're going to look at average fitness. And remember, the bar over a variable indicates that it's the average. What should happen to the average fitness over time? Well, selection has to always improve the population. So selection is going to be bringing our fitness up to some maximum point also. So now we're going to take a look at when do we reach that highest fitness? When do we reach the fitness maximum? And to do that, we have to look at what our frequency of P is and what our fitness is. So we're going to look at the frequency of the A1 allele P on our x-axis, it's going to range from 0 to 1.0, and then we're going to look at what our average fitness is. Now what we're going to do, rather than put actual values in here, we're just going to think about what the fitness points are and where they would fall on this map. Since P, the A1 allele, is the best allele, if we only have A1 alleles, then our fitness will be highest when our frequency of P is at 1.0. In contrast, our fitness will be lowest when we have no P alleles. And our fitness will be in the middle when 50% of our population have P alleles. So if we think about what our relationship is going to be, we'll see a nice straight line with fitness increasing as we go through. We'll see our fitness increasing as the frequency of the P allele increases. So no matter where we are, no matter what our frequency of P is, over time it's going to have to increase. And it's going to have to increase because natural selection requires that fitness always increases. So if we see a relationship here between fitness and frequencies of alleles, what's going to happen is fitness always has to move uphill. In essence, it's like the Greek mythological character Sisyphus, who spent his entire time rolling a ball up a hill. As soon as he got it up to the top of the hill, it would roll back down, and he'd have to start pushing it up again. This was punishment for falling in love with Zeus's daughter. Bad thing to do. You get punished. Don't do it. But what we'll also see is that over time, fitness always increases as well, up to whatever the maximum value is that it can. So now we've got a general idea about how the allele frequency should be changing over time. The frequency of the A1 allele, or P, is going to go up until it almost reaches an asymptote when we're selecting for a dominant. Now what we'd like to do is be able to figure out what is going to be the frequency of that P allele one time into the future. This prime here represents one time step into the future. So we need to think about what is going to be the frequency of that P allele one step in the future. Well, we know it's got to relate to the frequency of those individuals who are homozygous for the P allele and what their fitness is going to be. They're adding to frequency of the A1 allele in that next time period. The other individuals who are adding to it are the heterozygotes, who are going to have a fitness value as well. Now, notice, typically when we've been working with Hardy-Weinberg, we've always used 2PQ. In this equation, though, we're getting rid of that 2. Why are we getting rid of the 2? Fabulous question. Well, we're getting rid of the 2 because every individual who is heterozygous is going to produce only 50% of their gametes as P gametes, or A1 gametes. The other 50% will be A2 alleles, or the Q alleles. So essentially what we're doing is we're saying they are going to produce this many gametes, but only half of them are those we care about. Therefore, it's just PQ. Are you guys with me so far? Hopefully. Now what's going to happen here is that we have to scale this relative to what our average fitness is. We can calculate what the average fitness is as the frequency of the A1 homozygotes times their fitness plus the heterozygotes multiplied by their fitness plus the A2 homozygotes multiplied by their fitness. So we end up with being able to predict what the frequency of P is going to be one step into the future by using the equation P squared WPP plus PQ WPQ all divided by, sorry about that, all divided by P squared WPP plus 2PQ WPQ plus Q squared WQQ. And this equation will tell us what our frequency of P is one generation into the future. How does that help us now? Well, if we want to know then what the frequency of the individual genotypes are, we know that we can use our Hardy-Weinberg equation, P squared 2PQ and Q squared, to figure out what the expected frequencies of each one of those genotypes should be. And if we know what it's going to be one generation into the future, the P prime, we can figure out what the frequency of each one of those genotypes should be one time step into the future as P prime squared to get our A1 homozygotes, 2 P prime Q prime to get our heterozygotes, and Q prime squared to get the frequency of our A2 individuals. Okay, so I think that's enough for right now. We're going to stop this video and take it up again in another video as we keep extending how we end up using this equation.